All right, thanks everyone for coming to the last talk before the outing. I'll try to make it an easy talk. Um, great. So this is joint work with, oh, okay. So this is based on joint work with Harm Derksen and Nathaniel Johnston. So I'll start with the following very basic question. So you're handed a basis for a linear subspace of bipartite Hilbert space, Cn tensor Cn. And you want to determine if this subspace U is entangled, meaning that determine if it contains any product vectors inside. Okay, so this is an algorithmic problem. And this is a classical problem, and I'm going to be presenting classical algorithms for this problem. But it's motivated, this problem is motivated in quantum information theory. It shows up in a lot of areas. So really, an immediate application is what's called the range criterion for certifying entanglement of mixed quantum states. So if you have a mixed quantum state rho, if it's supported on an entangled subspace, then that state rho must be entangled. So it sort of gives you a polynomial time cheat to certify entanglement of, not polynomial time necessarily. The problem is actually NP hard. But anyway, it just gives you a certificate of entanglement of mixed states. These also can be used to construct entanglement witnesses and quantum error correcting codes. And they show up in other places too, like in like subadditivity of quantum channel capacities relates to these entangled subspaces. So today I'm going to be showing you an algorithm as well as polynomial time guarantees for that algorithm, for this problem, so classical algorithm, and then extending to other notions of entanglement, so certifying that subspaces avoid other sets, which I call X-tanglement. And then I'll be talking about a robust generalization of this question. Okay, so what do we know about this fundamental question? It's NP hard in the worst case. Okay. But there are some cases that are easy. So if the dimension of U is just too large, then it just has to contain some product vector in it, right? You just can't squeeze in too big of a subspace before you just have to contain some product vectors. And the magic number is n-1 squared, okay? So you can already tell just by looking at the dimension sometimes you can certify that you can tell if it's entangled or not. On the other side, right, so we're interested in this other regime where the dimension of U is smaller than n-1 squared. In this regime, if you pick U generically, meaning that if you pick a basis for U at random according to the Haar measure, then with probability 1, U will be entangled. Okay, so when I say generic in this talk, I mean that. So I mean, if you take a random basis with probability 1, the property will hold, whatever I'm talking about. Okay. So this talk is about a follow-up work to a talk I gave at QIP 2023, which was joint work with Nathaniel Johnston again and Aravind Vijayaraghavan. We presented an algorithm which either outputs fail or it outputs a certificate that U is entangled, okay? And we prove the following, so it's a polynomial time algorithm, and we prove the following guarantee for this algorithm, right? Of course, you could just always output fail. But we prove that we actually output a certificate in many cases. So if U is generically chosen of dimension 1/4 of n-1 squared, then it will be entangled, but you sort of want a polynomial time certificate of it, and our algorithm will give you a certificate. Okay, so this is like an average case polynomial time algorithm for the problem, loosely speaking. Okay. We also gave a related, so our algorithm also had this nice other feature, which is that if U contained a product vector, then the algorithm can actually produce that product vector. Okay, and we proved a similar guarantee. Sort of if you have a generic subspace with a generic planted product vector, we can recover that product vector. Okay, but in this talk, I'm going to focus on the certification side because it's sort of more relevant to the quantum computing in quantum information. Okay. Okay. So how do you approach this? How do you start thinking about coming up with an algorithm for this problem? Okay. Why is this difficult? Why is it NP hard? Well, one reason is that this set of product vectors is not so well behaved, right? It's not a linear space. If it was a linear space, then you just be intersecting two linear spaces, and you can do that in polynomial time. Okay. So the idea is instead we're going to make it linear in the most sort of naive way possible, right? I'm just going to intersect U with the span of all the product vectors, right? Of course, if that intersection was 0, then the intersection of U with the set of product vectors would be 0. This algorithm doesn't work, of course. This just never will certify entanglement of U because the span of the product vectors is the entire space. So this intersection will just always be all of U. But the idea is to lift this up to a larger linear system, that you're solving a linear system on a larger space. Okay? And up there, it becomes non-trivial. So I'm going to define this space except D, which is the span of the set of product vectors tensor D times. Okay? And if you rearrange terms, this span is the SD of Cn, the symmetric subspace of Cn tensor D. Like the U tensor Ds span the symmetric space, and the V tensor Ds span the symmetric space. So it has this nice, like, small description in terms of the symmetric spaces. And the algorithm, this lifted algorithm, is to check if U tensor D has any intersection with except D. Okay. And of course, and it's not hard to see that if this intersection is empty, then U does not contain any product vectors. And suddenly this becomes a non-trivial algorithm. Okay. Okay. I want to mention what's going on under the hood here is what's called Hilbert's-Null-Solensatz, which is a hierarchy of linear systems for solving polynomial systems of equations. And this is completely equivalent to what I wrote down on the previous slide. And I'm not going to talk about it much, but just under the hood, Hilbert's-Null-Solensatz is what we're doing. We're running Hilbert's-Null-Solensatz. Okay, so let's think about the first non-trivial level of this hierarchy. We're setting D equal to 2. Okay? And the algorithm is, right, if this intersection with U tensor twice with x sub 2 is empty, we're going to output that U is entangled, and otherwise we'll output fail. And this takes polynomial time to check. It takes time like, so these are spaces in Cn tensor twice, so it's n to the 4th dimensional space, and you're solving a linear system in an n to the 4th dimensional space. That takes time, order n to the 12th, okay? So, all right. All right, and this is correct. If you had a product vector in U, then the algorithm would not, this product vector tensor twice would be both in U tensor twice as well as in x sub 2. Okay, so this is a correct algorithm, but how well does it do? This was our result, was that this algorithm, if U is generically chosen of dimension up to 1/4 of this sort of cutoff regime that we care about, n-1 squared, then this algorithm will certify entanglement of U. I want to mention this is like, so I did the, I told you it was order n to the 12th algorithm. It's just solving a linear system, so you can do this extremely fast on a computer. So for example, the 10 by 10, for subsystems of dimension 10, the algorithm's running in like less than 6 seconds in MATLAB. Okay, so what does now get to for the present work? So we have this gap now, right? So we have this, I showed you this result of our Fox paper. We went up to 1/4 n-1 squared and basically had a polynomial time algorithm in the generic setting, or a polynomial time certificate in the generic setting for dimension of U 1/4 n-1 squared. This was extended by Dustadar, Waked, and Wine. Dustadar and Waked are 2 PhD students, and Alex Wine is a professor at UC Davis. They went up to 1/2 n-1 squared, and it's really nice. Their 1/2 actually still just uses the second level of the hierarchy, so it's the same algorithm. This intersecting U tensor twice with x sub 2. And then we have this like cutoff, right, n-1 squared, and beyond that, U just is never entangled. So what happens in between, right? This is sort of what this work is addressing. So question 1, is there a polynomial time algorithm for generic subspaces in the gap? And then question 2, what about the worst case, right? Can we, okay, it's an NP-hard problem, but can we come up with an algorithm that doesn't scale, maybe just has exponential scaling? Okay. So our first main result is that we basically extend this, this result to if dimension of U is like some constant fraction of n-1 squared, any constant fraction, then we have a polynomial time algorithm So if it's like a 1 minus epsilon constant fraction, we have an n to the order 1 over epsilon time algorithm, okay? Which is just the same hierarchy, running the same hierarchy, improving at what level you need to go. And then in the worst case, I've actually been a little more refined in the statement. So this is when you have two different spaces of dimension n1 and n2, and I'm stating what you get there. So you have an n1 times n2 to the minimum of n1 and n2 time algorithm in the worst case. So this is nice because if one of the two spaces is constant dimensional, you actually have a worst case polynomial time algorithm for this problem. Okay. Okay, so the whole thing generalizes actually to what are called algebraic varieties. So where you replace the set of product vectors with a different set. That's what I'm going to do now. And that different set is going to be like a set of states that is of some low entanglement, like states of low Schmidt rank or tensor network states of low bond dimension, something like that. In general, it'll be any algebraic variety. So an algebraic variety is a subset of Hilbert space that is defined by a set of polynomial equations. Okay? So for example, the set of product vectors is an algebraic variety. Okay, so let's see this. So it's defined by degree 2 polynomials of degree 2, polynomial equations of degree 2. And here they are. Okay, so there's polynomials. These are degree 2 polynomials in the entries of the vector psi. Okay, and where do these come from? These are so if you think of if you think of bipartite Hilbert space, if you think of it as if you think of Cn tensor Cn as the space of n by n matrices, right? Then a product vector is just a matrix that has rank 1. Okay, and so and then it's a standard fact in linear algebra that a matrix has rank 1 if and only if the determinant of every 2 by 2 submatrix is equal to 0. And so that's those determinants, those 2 by 2 determinants. I've written them down here. They're polynomials in the entries of the vector. Okay, so product vectors are defined by polynomials. The set of product vectors is exactly the set of vectors at which all these polynomials are 0. And it turns out there are many notions of many sets which characterize low entanglement, which are notions of low entanglement that happen to be defined by polynomials. Okay. The set of product vectors I've mentioned, the set of Slater determinants, which shows up in quantum chemistry, biseparable vectors, L-separable vectors, all these different sort of things that pop up when you're studying genuine multi-party entanglement instead of complete entanglement. Tensor network states, if you fix a graph and you fix the bond and you want to know the set of tensor network states of a given bond dimension, those form a variety, an algebraic variety. The set of stabilizer states form an algebraic variety, and more generally, any finite set of states. Okay. So this gives you a lot of structure actually when you have these when you have a set that happens to be defined by polynomial equations. Okay. And so we're going to use that structure for this more general problem where you're handed a basis for a linear subspace of some Hilbert space, and you want to see if it avoids, if it intersects X, where X is some fixed variety, for example, the set of product states, the set of Schmidt rank at most R states, the set of matrix product states of limited bond dimension, the Slater determinants, many examples that this, and sort of, these all have sort of analogous applications as I showed for the standard entangled subspace problem. Okay, so more generally, we prove that for all of these examples I've mentioned, we get a similar genericity result. That for a generic subspace of dimension, a constant multiple of, this should just be a capital N, not a capital N squared. We're just living in capital N space. So a constant multiple of the total Hilbert space dimension. There's a polynomial time algorithm to certify that the subspace avoids X. Okay. And in the worst case, you get an exponential time algorithm, but we can write it down what, exactly what level of this hierarchy you have to go to. I want to, again, let's focus on the, or I haven't done this yet, but let's focus on the set of Schmidt rank R states. In this case, you get an analogous result as I showed before, where you have a worst case algorithm that runs in the following time, n1 times n2 to the order r times min of n1 and n2, where I'm considering now potentially unequal subsets dimensions. And once again, this is polynomial time. This gives you a worst case polynomial time algorithm for this problem when one of the two subsystems have fixed dimension. Okay. So what's the algorithm, right? It's just a straightforward generalization of the one from before. You're turning your intersection problem into an intersection problem for linear spaces. So instead of asking, it's hard to check if U has any intersection with X, but it's easy to intersect linear spaces. It's easy to do that. And so what you do is you define this lifted space associated with your variety. I'll call it XD, which is the span of the set of psi tensor D as psi ranges over X. And then you just check if U tensor D has any intersection with XD. Okay? I briefly flashed the proof, and yeah, so it uses some well-known results in commutative algebra and algebraic geometry. I guess my point in showing this slide is like there's a lot of structure for sets that are defined by polynomial equations, and these things have been studied for centuries. Zeros of sets of polynomial equations. And sometimes you can get some of these algorithmic results for free from things that have been known, just old theorems. There's a lot of structure that's been discovered about these sets. Okay, so now I'm going to move on to a robust generalization of this problem. Okay, so first I'm going to review what's called the symmetric extensions hierarchy. So yeah, so if you've if I've lost you, this is a great place to come back to the talk because it's sort of a reset of the talk. So once again, we have sort of a just basic question. So you fix a Hermitian operator W on some bipartite Hilbert space, and you want to compute its maximum inner product over over product vectors, okay? Maximum expectation value with product vectors. So this gives you in particular, if you could do this, you'd be able to solve a robust version of the entangled subspace problem by setting W to be the projection onto the subspace. And then this tells you what's the maximum overlap of your subspace with a product vector. So the overlap would be 1 if and only if U contains a product vector, and if, however far away it is from 1, that'd be that distance away from product vectors. So this is why I call this a robust generalization of the task. And it's the dual to this well-known separability problem. Okay, so it's like essentially the same thing. Like if you have an algorithm for this, you have an algorithm for the separability problem, which is you're given a mixed quantum state and you want to determine if it's separable or not. Okay. But I'll focus on this sort of optimization version in this talk. So in 2004, Doherty, Perillo, and Spedalieri came out with a hierarchy, again, a hierarchy of, so it's an NP-hard problem first. It's an NP-hard problem, but they came up with a hierarchy of eigencomputations for approximating this maximum inner product. Okay? Okay, so, all right, so they define some, it's a little complicated, but again, you see that this space except D is showing up, right? And you're sort of, yeah, you're taking the maximum eigenvalue of something. Let's focus on the case little d equals 1. Okay, so when little d equals 1, all these things go away. You're just computing the maximum eigenvalue of W. Okay, which is of course an upper bound on the maximum inner product of W with all product vectors, right? Because the maximum eigenvalue is like the variational characterization of the maximum eigenvalue. Okay, so mu1 is an upper bound on W star. And it turns out that these mu d's form a non-increasing sequence. They converge down to W star. This gives you a hierarchy of eigencomputations that approximate W star arbitrarily well. And then moreover, what's called the quantum Definetti theorem gives you a bound on the rate of convergence of this hierarchy. How fast does this hierarchy converge? How good is the D approximation? And the result is that the difference between mu d and W star is less than or equal to 8n over d plus 1. And the key is that d plus 1 on the bottom, right? Because as d goes to infinity, this is going to 0, and mu d and W star are going to be equal. or mu d will approach w star. Okay, so if we turn this around to, I'm sort of going to mention sort of the separability side of things very briefly. So if you turn this around, you get like what's called the symmetric extensions hierarchy for separability, where it says that a mixed quantum state is separable if and only if it admits a symmetric extension, a d-symmetric extension for all d. Okay. And what is symmetric? Symmetric is this symmetric subspace. That's why it's called the symmetric extension. This doesn't work. Okay. Okay, so yeah, this is sort of, you can generalize this, this symmetric extensions hierarchy to an arbitrary optimizing a Hermitian operator over an algebraic variety. Okay. So for example, optimizing a Hermitian operator over a set of tensor network states of a given bond dimension, et cetera. Okay, and it looks almost exactly the same. I've replaced the symmetric subspace with this space XD. Okay. Is that it? 5. Okay, thanks. Okay, so that's one result. As sort of a bonus, we were able to prove a quantum definite Eddy theorem for optimizing over Slater determinants. Okay, these Slater determinants are anti-symmetric vectors that are the wedge product of some vectors. And we prove a similar convergence for this hierarchy in that case. And a proof sketch is that this space, XD in that case, happens to be an irreducible representation of the unitary group. It turns out that like this, the proof of the quantum definite Eddy theorem, if this lifted space happens to be an irreducible representation of like some group acting on your space, then you sort of get a quantum definite Eddy theorem for free. Okay, so one interesting corollary is we get a hierarchy for optimizing over this set of Schmidt rank R states. Okay, and this seems to sort of heuristically, we don't have a proof yet, but it heuristically seems to outperform a previous hierarchy for optimizing over Schmidt rank R states that was developed originally by Nathaniel Johnson in 2012 and has been studied in several works since. This is a particularly interesting case because optimizing over Schmidt rank R states is highly related to the NPT-bound entanglement problem. In that, like, the Werner state is k copy undistillable if and only if its partial transpose tensor k, when you optimize it over Schmidt rank 2 states, you're non-negative. So it's sort of a, because of this application to NPT-bound entanglement, it would be really nice to find, this is sort of an open problem, the main open problem that I want to pose that I'm very frustrated with. Can we prove a quantum definite Eddy theorem for optimizing over Schmidt rank 2 states? Okay. The problem here is that the space is not irreducible. So if this XRD, you see, I've written it out in terms of Schur modules. It's not an irreducible, it's not irreducible, right? It has this decomposition. Okay, so that's all I have for you. So I've told you about some polynomial time algorithms for certifying entanglement of subspaces, and as well as a generalization to the robust case. These are the 3 papers that this talk was based on, in particular the 3rd one. And I want to mention I'm looking for graduate students. I'm at Concordia University in Montreal, so come live and work in the heart of downtown Montreal. Thanks for your time.
Hey, thank you for the talk. I was wondering if we consider any property labeled by X that suits your formalism, that it's variety. Is it clear that you always have some subspace that completely has this property of dimension larger than 1?
Yes, so you can determine what the maximum dimension of such a subspace is by the dimension. So there's a notion of dimension for varieties, and it's the complement of the dimension. So just like for subspaces, if you have a k-dimensional subspace, the maximum dimension of a subspace that avoids it is n minus k.
Okay, but there's a maximal dimension, but do they exist?
Yes.
They always have to exist.
Yeah, they exist and they're generic too. So if you take a random subspace of the complementary dimension, it'll avoid the variety.
Okay, thank you.
Yeah, thanks.